All right. Good morning, everyone. So last week we talked a lot about different data types in Python, mostly the fact that there are different data types, and it's really important to know what data type you're working with so that you can work effectively. So last time we focused on strings, which is like any sort of characters and text, and today we're going to shift focus and start talking a little bit about numeric types. So I'm going to go ahead and move this to another screen and open my text editor here. But all of you should be able to follow along with what I'm doing. So one moment. So we should be able to navigate to Python focus group together. Remember, if you type PFG at your terminal, we created an alias, so it should just take you straight there. And I'm going to navigate to session 6, and I recommend you create a session 6 directory. And I'm going to make a file. So we're going to say touch numeric types.py. So now I see numeric types.py has populated here. So I'm going to go ahead and open that up. And as per usual, I will copy my interpreter directive and we'll start going from there. So one of the most straightforward types is an integer. So I'm just going to copy over from that markdown file different types of integer examples. So we can say print int1, for example. So now if we run python 3 numeric types.py, it's just printing the output of that type. So it's saying, or the variable. So it's 1. If we switch this, let's say, to 5, it's now going to print the stuff in int 5. Now, one thing that's really particular about integers versus different types of numeric types in Python is the formatting really matters. So, for example, if you want to learn the type of something, you can actually use a function called type. So I can say print type, and this will tell you the data type. So I can say print the type of int 5. And so now type int 5 is the inner function, and then print is the outer function. So we have to make sure to wrap all the parentheses accordingly. And now if we run this, it says class int, meaning it's an integer. But one thing we know is we read in a data set, a data frame of some sort, and this is punctuated with all the numbers like this. So 21,543,215, or 21,543,215. Like this is a pretty standard way for us to look at numbers, but Python does not see it that way. So all of a sudden, just by putting these commas here, it switches the class to tuple, which means it is actually taking each of these and considering this a separate item. So when you're working with integers, you want it to be exclusively numbers, meaning no commas, no periods, nothing. That's how you stay as an integer. So there we go. So that's how you stay as an integer. So one thing that's kind of funky about Python is there's also something called a float. So notice that here is a bunch of different variations of decimal points. So there's like 1.0, 3.4, 9.999. There's also divisions. So like if you have what looks like something dividing, it will just do the calculation and call it a decimal, which we call a float. And we can see that all of these are very similar to integers in that we can use them for math and manipulate them in similar ways, but Python still classifies it a little differently. And one weird thing about Python I do want to show you is that if I say type int 1, and then we look at the type for, let's say, float 1, which should just be 1.0, and print that, one is classified as an integer and the other is classified as a float, despite the fact that this is 1 and this is also 1. So one thing you need to be careful of, especially when you're starting to read in like data frames and things like that, is make sure that the type in each column matches what you would expect it to. Remember last week we had that example where if you have the number three and you multiply it by three, it just becomes 333 if it's a string, which is not accurate. So the reason that I'm trying to show you the different data types that exist is because you can do different types of operations on them depending on what you need. And certain operations work and others don't. And it used to be the case, I will see if it is still the case, but it used to be that you cannot add to like an integer and a float, but I believe they changed that in recent times. Yeah. Now it just converts the integer to a float. But it used to be that you would have to change it yourself before moving forward. But in order to change that, we're going to talk a little bit later, but there are functions, and it's called typecasting, where you're able to say, I want this to become an integer. I want this to become a string. And within reason, it works in some directions and not others. Like it's easy to turn any of these into a float, but it's hard to turn, or it's easy to turn these into floats. It's easy to turn these into strings, but it's really hard to turn something like string one equals example. It's really hard to turn this into an integer. You can't really do that. So just be aware of what data type you're working with. So I am briefly going to show some information about complexes. I used to actually go into this and teach it in more depth, but even to date, now that I've been coding for like some 6, 7 years, I have literally never used this. So I don't think it's worth trying to confuse you all a little too much. But just know that if you are doing any sort of math that involves real imaginary numbers, you can use complexes. There's real parts of the number and there are imaginary parts of the number, and they're represented in different ways. And I have provided some sources here for you to look into it more deeply if you ever need it. So, just to quickly touch, like the purpose of this course is to provide you with a tool set so that you know what tools exist in the language. You don't need to memorize every single aspect of it, every syntax mark, every function. It's just so you can think, oh, I remember there's a way that I can do this. Let me Google it real quick and see what that function was. That's the kind of information that I want you to walk away with. So, for the sake of this section, you can do math with imaginary numbers, and that is all the takeaway I want you to have from that point. So, moving forward to the data casting. So, we're going to have some examples of different data types here. So, this is an integer. An integer follows the typical math definition, by the way. It's just any whole number. And then you also have the float, which is some sort of decimal point, and you have a string. So first, let's all try to see the type. So we can say print type of A, type of B, and type of C. And notice that print, you can have multiple arguments. So you could just separate those by a comma and it will print everything out for you. So as we expected, it's integer, float, and string. So integer, float, string. Now I want to show you why knowing the types are important. So we can do print A plus B, and this should be fine. So this gives us 2.5, so 1 and 1.5 works. But if we do something like print A plus C, we know that 1 plus 1 is 2, but Python doesn't know that. So it will tell you there's an unsupported operand going on. It doesn't like this. It's saying you can't do this. You can't add an integer in a string. So what happens when we run into something like this? Well, the easier way that we can do this is to just typecast. So there are some different functions we can use. In the case of C, we can see, let's see if we can turn that into an integer. Yeah. So if you put int C, int tells Python to treat this value as an integer. And since this is a valid integer inside the text, it can do that. So like if I do something like D, then it will yell at us. It'll be like, yeah, you can't really turn D into an integer. But even though it's a string, as long as it is some sort of actual number, we can typecast that to an integer. And that works fine. So we can see that we can add that. This is most typically seen when you load a data frame. So we'll be doing that in a few sessions, but generally when you load a data frame and it's something called head. So you look at the top of the data frame, it'll show you for each column what data type you're working with. So it's really good practice generally to just look at each column and be like, is this what I would expect? Because you don't want to take the average of a column. You don't want to like log transform a column only to realize you're not working with what you think you're working with. So yeah, um, in to demonstrate some other things we can typecast. So other functions for typecasting, and this is still from the notes if you're following along. We can turn strings into integers like I just demonstrated with one. So I'm going to comment this out really quick so we can take it one piece at a time. So we have an integer and we're typecasting it using the int function. So saying int 3. So now if you print my integer, it'll give you 3, which is the value stored in that variable, and then tell you that the type is an integer. So if you want to turn something into a string, you can also do that. So if we have 53, notice how it's red. Going back to that syntax highlighting stuff. The 53 is red. Anything that's a string is this kind of gray color. Numbers here are red. So we know that this is a number, and we're going to turn 53 into a string. So we're saying let's turn this into a string and then check what the value is and then the type. So now it's saying it's 53 and the type is a string. So we have effectively turned an integer into a string. Another thing you can do is use the float function. So you can turn 7, which is just an integer, into a float, so it should be 7.0. So if we do that, we get 7.0 and the class is a float. So the real things I'm trying to point out here are there's 3 functions, int, string, and float, and these are the functions that you can use to convert between these different data types. And this is important for any sort of math you're doing, which we'll dive into right now. But yeah, this is important for any type of math you're doing, and we talked more about the strings last week and why it's important to have certain things formatted as strings. So if you need to check the type of a data frame, you can just use this type function. And if you need to change it into a different data type, you can just use the data type itself as the function, and it will convert to that data type. So yeah. Um, all this time so far, I've been talking about doing math with all our stuff. Like, we're going to have to do operations and do math and like calculate things. And so now we can dive a little bit into what that actually looks like. So I'm going to briefly go over the different types of operations you can do in Python. And some of them seem pretty straightforward. Some of them are kind of weird. So plus is just addition, minus is subtraction. Instead of a time symbol like the little X, we use an asterisk to do multiplication. If we do division, we just do the typical like back forward slash one of the two slashes. Floored quotients, so I believe this is where it just drops any remainder. If you want to see what the remainder of something is, you can use this percent symbol, and this is called modulo. I'm going to give a quick aside about modulo because I remember when I was learning about it, I thought it was the most unnecessary thing I've ever thought of. I was like, why would you need to know the remainder of something? But as I started coding, I realized there are some weird cases where you're like, oh, I specifically want to know, like, is this divisible by 5? And if it's divisible by 5, for instance, then the remainder is 0. So you can code something like if x modulo y equals 0, then you're able to determine if it's a multiple of something. And this is important, say, in like FASTQ files. So FASTQ files, briefly, let me bring that up. So FASTQ files always have 4 lines. So the top line is the header, The second line is the sequence. The third line, it's always a plus, and I don't exactly know what that means or why, but it's a plus. And the fourth line is ASCII2 Q scores. So this is basically like a representation of the sequence quality per base, like per base pair, like how confident you are that each base pair is a base pair. So one really, really easy way to check the number of sequences that you have in a FASTQ file is to use something like the modulo. Be like, as long as the modulo is zero, we can see what number of fast, or if our FASTQ file is not corrupted, for instance. Like it has all four lines for every single entry. So if you say like FASTQ file length divided by 4, you want the modulo to be 0. So that sounds a little complicated, but it can be helpful in instances like that. So that's something that we can do. You can just put a negative in front of something and it'll turn it negative. If you need the absolute value of something, there's a function called abs, which is just absolute value. We've already talked about integers, floats. This is for the complex numbers, so like the real versus the imaginary part, which just there is a function you could work with. And then you can also do some other stuff. So like if you want to do x to the power of y, there's two ways you can do that. One of them being a function just called power, so x to the power of y, or instead you can just put two asterisks. And the reason we need two is because one is multiplication. So two does an exponent. I think I have it a little later. PEMDAS? Yeah, okay. I'll get there eventually, but one thing I want to highlight is everything in Python follows typical PEMDAS, like back to our algebra days, like product, exponent, or parentheses, exponent, multiplication, division, addition, subtraction. So it will execute in that order. So if you're doing any sort of complex calculations, you need to make sure to use parentheses accordingly because it will execute exactly what you tell it to otherwise. So let's look at some examples. Sorry, I'm about to sneeze. Okay,
Bless you.
thank you. So we'll go ahead and look at some different examples of expressions now. So I'm okay with exiting numeric types, and we'll create a new file and we'll call this expressions.py. You don't have to, you can. It's mostly for my own organization's sake. So expressions.py. So here we see a bunch of just random numbers, and you can keep these numbers, you can change them, you can functionally do whatever you want with them. So here we're just going to look at the sum and see how you compute the sum. So we'll say Python 3 expressions.py. And remember last week we learned a little bit about f strings. So here we're saying f, and then in the print statement we're putting our variables. So we're saying the sum of a, so we can see a, and b, which is b, is a plus b. And since this is Python code embedded in those little curly brackets, it's going to compute the calculation. And that's what we see. So it says the sum of 10 and 5 is 15. So you can do something similar, but find the difference. So we can say find the difference, and the only difference between those is we've changed the plus for a minus, and we say now the difference between 10 and 5 is 5. So yeah, I imagine you all know how to do math, but it's mostly the syntax we're focusing on here. So let's say you want to multiply some numbers. We use the asterisk to say A times B. So we say the product of 10 and 5 is 50. If we want to divide it, we can divide it. So A divided by B, so 10 divided by 5 is 2. One thing I want to show here too is that when you're doing the division, it oftentimes will convert this, even though these are integers, into a float because division will most times not be perfect like that. So if we do, let's say 10 divided by 3. So if we do 10 divided by 3, so we'll substitute that out for C. and it will still calculate the difference. So we'll say the quotient of 10 and 3 is 3.333333333, whatever. So yeah, it'll turn it into a float. So now we can do the floored quotient. So notice when I did the 10 divided by 3 here, it did 3.33333. If you just put two slashes, so instead of one slash, if you just put two, it will drop every single thing after the decimal point. So this is helpful. I don't know if you remember in algebra those like word problems where it's like, how many people can you fit on a boat if you have like 20 people and three boats or something like that? Like in some cases, you need the nearest, like not the nearest whole number because you can round, but like you need, how do I explain it? Like the number without the decimal portion of it. Like that's the maximum you're allowed to fit in a certain scenario. So that's called the floored quotient. So basically, it just drops everything after the decimal point. It's like your number is 3. There you go. That's it. So the floored quotient of 10 and 3 is 3. So now to demonstrate, this is the modulo situation. If we want to find the remainder itself, like the stuff that comes after the 3, we can use that modulo symbol and it'll tell us what the remainder was. So I think it rounded. Um, but it says like 3.0.333. The modulo is always an integer, so I think it rounded to 1. There's all sorts of other things. We can look at negative numbers by literally just putting a negative. So D is negative 19, but if we put a negative to a negative 19, it will turn it positive. So it says when we negate negative 19, we get 19. If we want to find the absolute value of D, which is a negative number, the absolute value of negative 19 is 19. So we do that with the absolute value function. And then we can also do like exponents. So a to the power of c, you can use this power function. So pow ac, and it will do 10 to the power of 3 is 10,000. But I will admit I never actually use that function. I just do the two asterisks. So I do a asterisk asterisk c, and we get the same thing. Now, one thing I want to highlight is with all this stuff in Python, I think I mentioned it in one of the earlier sessions, but Python is actually forgiving when it comes to spaces in your code. So you can space things accordingly. So if I like my expressions to have spaces because I think it looks pretty. Not everyone thinks that. There's also just being succinct if you need to. So we can remove all these spaces and it will do the same thing. So we do that and we get the exact same output. So again, there's a lot of stylistic preferences that you can have when you code. I like spaces. I like it looking easy to read. And that's actually a power of Python, is being able to look at the code and just kind of read it as close to English as you can see. Um, Older code used to be very obscure looking, if anyone's seen like C itself or C++. Like there's a lot of more obscure words and functions and things like that, whereas Python was designed to look more straightforward and be more similar to how people think. So I've talked about that. So these are all simple expressions. It's just like one operation versus the other, but we can do more. So this is an example of where PEMDAS would get implemented. So we have expression 1 where we have a times e, so it would be 10 times 2 plus negative 19. So PEMDAS kicks in and the computation comes out to 1 because 10 times 2 is 20 minus 19 is 1. So we can see if we want to switch this, so instead of having a times e plus d to have 1, we can do a different expression and put parentheses around e plus d, and this will prioritize that computation instead. So now instead of 1, the calculation is negative 170. So just make sure that when you're doing different expressions or mathematical operations, either take it one at a time. Like what you can do here is say, we can just assign a new variable temp d or something like that and say e plus d and then use the variable here. So like temp d. And if we do that, it will still give us the same number. So again, stylistic preferences, you can either do the calculations one at a time or you can put them all in like one single line. It's really up to you. There's a lot of flexibility here. So one example, let's say we want to determine how many hours this many minutes is. So 43 minutes plus 42 minutes plus 57 minutes is how many hours? Well, again, you want to have informative variables. So we're saying the total number of minutes is the sum of this. The total hours, so the total hours is the total minutes divided by 60. And now we can print total hours. So we're doing math and finding that 43 plus 42 plus 57 minutes is roughly 2.3 hours. So yeah, um, there's also something that will be relevant shortly, but for now, I want to show you that you can do iterative things like shorthand notations with math. So we're going to say practice. It's called simultaneous math assignment. So we'll set a variable I equals 0 and then say I equals I plus 1. So this is kind of recursion. So for example, if you are running a loop and doing something over and over again and you need to know how many iterations you're doing something, you could do something like this, like I equals 0 and then add 1 and then at the end your I will have changed. And I think there are examples of that in this session and where that's relevant. But yeah, so we can say print I, and we should see that I is 1 because it was 0 and then we took 0 plus 1. So you're able to actually reassign the variable and overwrite it. So this takes precedent as the original variable. So this is substituting I as 0 and then assigning that value to the variable I, which overwrites the previous I. But there's shorthand notation. So we can say I equals 0 and then actually say I plus equals 1. So this is the shorthand notation. And when you do plus equals, what it's doing is taking it and saying I plus I, or I equals I plus 1. So it's literally just shorthand notation for this. So if we print I again, we should see the same thing. And we do. So I is 1. This is one of those things that like it's pretty like hardcore coders do it this way kind of a thing. There's absolutely nothing wrong with just doing this way. Like it's just for your information so that if you're looking at someone else's code or trying to understand someone's code and they're doing this, just know that that actually means this. You don't have to code it yourself, just understand that that's what it means. So we're going to try doing some more complex math now. And this was just the basic built-in Python function. So this is all native Python language. But typically in Python and just other languages, you're going to have people who build upon the language. And that's the strength of having languages, right? Like in R, you have people who make new packages for R, and then you're able to load them into your R environment and run those things. In Python, similarly, people build packages and they're called modules, and you can read those in and use the functions from there. So I'm going to clear this and touch, we'll call this complex math.py. And again, you can keep it in the same thing. I'm just going to start a new file because it's prettier that way for me. So we will put our interpreter directive, and then we're going to import a module. So you might, if you're familiar with R, know that usually it looks something like this. You'll say library package name. In Python, it's similarly simple. It's just import and then whatever the package name is. So import, in this case, it's actually called math. So it's just basic math, but with more intensive operations that you can use. So we import math, and if you run it, so Python 3 complex math, nothing happens because all we've done is import. We haven't expressed having any sort of output. So no issues there. Some modules are pre-installed as part of your Python install. So one of the reasons I wanted to install Python with Conda is it has a lot of built-in packages and native Python libraries that come with it. And I think that's true even if you just download Python as is, but it means that you don't have to install it. So in a few sessions, when we start actually diving into a data frame, we will be having to install packages ourselves, and that's when Conda will become a little more relevant. But right now, math is just something that we can access as needed as part of Python. So now let's say we want to do the Pythagorean theorem. So remember our a squared plus b squared equals c squared situation. And the classic example of that is a is 3, b is 4, and c would be 5. But in this case, let's say we want to print our hypotenuse length. We're going to use the square root function. Now, this is where it gets a little dicey. Previously, it was pretty straightforward. I'm like, you want to add something, use plus. You want to subtract something, use minus. How do you do square root? There's no square root symbol on the keyboard. So that's where we actually use something from math directly. So we say in the math module, so we say math dot, and then there's a function called square root. So SQRT, square root. And then we can do a squared, which remember, a to raise to the power of something, you do two asterisks. So a squared plus b squared. So b asterisk asterisk 2. So this will take the square root of a squared plus b squared. So now if we print the hypotenuse length, that should give us 5, which it does. So this is how you would do square root. One of the more commonly used ones is a log2 transformation. So like log transformation. This is helpful for like normalization of RNA-seq data, for visualization using like p-values and things like that. So in order to do that, we can say print, and then again, we're accessing a function in the math module, so we have to start that with math dot, and then log2 is the function name, and we can just say 0.25. So this is going to calculate the log base 2 of 0.25. So we get -2. So you can also use all sorts of other things in that's like math related that aren't really intuitive in terms of like how to type it on the keyboard. That's where the math functions come in. So if you want to use pi, you can say print math.pi, and you literally just say pi. Whereas, just as an example, if I just print pi, it's going to yell at us. So here it prints the actual pi, but then once it gets to line 17, which is the print pi, it's like, yeah, I don't know what you're talking about. There is no pi. So this is why putting the math in front of it is important. It's able to get the value of pi. So this is really nice because you don't need any approximations. It will do it to the best extent that it can with the whole number. There's also Euler's number. So you can say like print math.e if you remember that, and if you don't, then you probably don't need to know what Euler's number is anyway. But yeah, you can access that. If you need some sort of infinity, you can say print math.inf. So that's infinity. And it does not print anything specifically. It just prints inf, meaning infinity. And you can also do factorials. So say compute factorial. You can say print math.factorial and then like 3, for instance. And it will print the factorial of 3. So these are all more complicated mathematic calculations that you can do. I think for us, the most relevant ones are typically going to be like log transformations. Maybe that. I think I've used square root on occasion. I haven't really felt a need to use these things, but it's nice to know that if I needed to do more complicated mathematics, I have access to those things using the math module. So that concludes our math stuff for today. Thank you for coming to my math lesson. So we're actually going to shift now to maybe why it's important to need these types of numbers and expressions and things like that. So we're shifting a little, if you're still following, I'm going to send that again. Still the same session, but we're going to shift from all our math and numeric types to sequence types. So these are our tuples, lists, and ranges, which go a little bit hand in hand with the math stuff. So I'm going to create a new file, and I'm going to call this tuples.py, and I'm going to open that up. So remember in the earlier example, I showed that if we had like that number and separate it by like commas, it treats it as a tuple. Now we're going to learn what a tuple actually is. So a tuple looks just kind of like a list. So we can put stuff in it. We can say like disco 10, 1.2. And the reason I want to show you this example is here in this data type, we're in one variable, we're storing three different data types. We're storing a string, an integer, and a float, all in one thing called tuple1. So if I print tuple1 or tuple1, and then let's just see the type. So type of tuple1 should tell us that it's a tuple. Oh, to run the thing. There we go. So we print tuple1 and it prints this out for us, which is what tuple1 is, and it tells us the class is a tuple. I think some people call this a tuple. I actually don't know how it's pronounced, and I've heard it both ways, so we're just gonna hope that I'm doing it right. But yeah, so this is a tuple. And remember, we talked a little bit about indexing strings before. So this was using that weird like 0 to like not 3 notation or whatever. So that's going to come back because we use that same style of indexing with tuples as well. So in order to index tuples, we'll say first element. So throwback, if we want to get disco in return, that's the first element of our tuple. How do we do that? Well, same as string indexing. We put tuple1 and then we give it the location. So remember zero-based indexing. So this is position 0, 1, and 2. So we can say position 0. And now if we print first element, it should just print disco. And it does. It prints disco. So now I think I had shown you guys a little bit about like the -1 means the last element. So we can also print the last element. So we can say like print tuple1 -1. And instead of printing an actual -1, it's going to print the last element in the tuple. So it's going to print 1.2. So it's the same exact thing as string indexing. And fun thing, if you actually want to count backwards, you can do that. So you can go -1, -2 will print 10. That's something that's also weird. So you can go in both directions. Generally, nobody does like anything but -1, but you can do that if you want to. So there we go.
I had a question.
Yeah.
These tuples, are they considered objects, or how is it different from like the object-oriented programming?
Yeah, so these are actually objects. So that's a great question, Nick. So generally Python takes an object-oriented programming approach, meaning that everything is in itself like an object or a class, and then within that you have attributes that are attributed to those specific classes. So a tuple is actually its own type of class and object, and that's why there's certain functions and like things related to tuples that we're going to be talking about a little later. So, like, we can sort tuples, for example. We're able to index them because those are all properties of the tuple class. So,
Yeah, thank you.
yeah, no problem. Okay. So, we're going to look at some different ways of indexing, and I'm just going to copy this over because it's kind of long. This is again in the reader, but this is just different genres of music. So pop, rock, soul, hard rock, soft rock, R&B, progressive rock, disco. This is just a bunch of different genres. If I wanted to find the index of something, I can actually just do that by saying print genres tuple. So that's the name of this object. So genres tuple dot index, and the index will is the function that is going to tell me what the index is, and I'll say disco. So it tells me disco is the seventh index. Now, if I want rock, we know that this should be 0, 1. So now if we do this and say rock instead, it should print a 1. And it does. So again, same as string indexing, except instead of a string, now we're looking at each one of these separated things as its own element. So briefly, I won't give, no, I'll just give an example. It's really quick. So I think I was showing you guys we can, like slice strings, like you can take elements 1 through 3, for example. You can literally do the same thing here. So you can say like print genres tuple, and then we'll say element 0 to 3. And it will do the same thing as first string. It'll just return the first 3 elements of that. And then if you want to do the same thing as like a stride, the stride is like print every second element. So you can say from like the first to the last thing, print every second item. You can do that too. So it's exactly the same as string operations, but it applies with each of these as its own element. So one thing we can do with tuples is sort them. So we're going to use the sort function. Here, I'm going to do a tuple called ratings and just have a bunch of numbers in it. So then we're going to say print, and then here I'm going to do my F string setup. So print, and then in the F string, the original tuple is, and in squirrely brackets, or curly, I say squiggly and curly, and it comes out as squirrely. In curly brackets, we'll say ratings. So now if we print that, we'll see the original tuple is, and it just prints the whole thing. And fun fact, I didn't put any spaces here. It printed with spaces here. So back to Python doesn't really care too much about spaces. But now we can say ratings sorted as a new variable and say sorted ratings. And now print, we can say another F string and say the sorted tuple is ratings sorted. So now, notice it's sorted in order. So it goes 2, 5, 6, 6, 8, 9, 9, 10, 10. So this is something that's helpful if you're doing, let's say, making a histogram, for example. A lot of people, when they generate a histogram, they want to see the highest like bar at the front and then descending in order. So having your data sorted can be really helpful for that reason. Now, I want to show you something quickly too. So a tuple, notice that all our tuples are surrounded by parentheses. So it says the original tuple is, and this has parentheses. But now we see the sorted tuple has brackets around it. So that's actually very deliberate. So let's check the type. So we'll say print, and we'll do type of ratings, and then we'll print type for ratings sorted. For ratings, the type is a tuple, but for ratings sorted, the type is a list. So it's just important to know those are 2 different data types, and that's because in order to sort something, it's like Python turns it into a list behind the scenes. So always know your types. Um, so now we're going to go to concatenating tuples. I'm going to go through some of this a little quickly because I want to get to the lists because lists are a little more helpful in my experience. But concatenating tuples literally just adds these things together. So if we have like disco 10, 1.2, and then we add this with hard rock and 10, it's going to just print the whole thing out. So it just adds it all together. So you get disco 10, 1.2, hard rock, and then 10 again. And you can also nest tuples as well. So here If we have a nested tuple, we have one, two, and then within the tuple, we see another tuple. So the indexing for this starts becoming a little more complicated because if we want to access this element as its own tuple, we can say print nested tuple, and then this is 0, 1, 2. So this is the second element, and now it's going to print that whole thing. So it's going to print pop rock, and pop rock is right there. But what if you want to get just pop? How do you do that? Well, the fun thing is you can literally just tag on another element. So you've already reached pop rock. Now we want pop. So within this element, pop is the first thing, which is index 0. So if we put index 0, now it just prints pop. And we can actually do it as granular as we want within reason. So like now we have pop. Pop is just a string. If we want the P in pop, we can also just add another 0. And now it just prints the P in pop. So you can zoom in or out just about as much as you want with indexing, but if you do this on an element that doesn't have these things, it's going to tell you it's out of bounds. So like if I do element 0 and then try to nest any further, we can't really do that. So it's going to say int object is not subscriptable. So yeah, it's like there's no further indexing that can be done with this. But let's say we use this element. So this is -1. It's the last element. And then it's going to do the 0th element and then the 0th element. So it should print a D, which it does. So you can zoom in and out of different data frames and data types like that. So as I showed you earlier, the type of ratings sorted is a list, and lists are very, very similar to tuples, except the big difference is, believe it or not, you can't actually edit a tuple after it's been created. Like you can't add elements without creating a new item. So like here, I had to do tuple one plus tuple two to give tuple two. I couldn't just add something already to tuple one, whereas lists are different because you can add things. So let's switch to saying lists and we'll create a new file for this. So we'll say touch lists.py and we'll open our lists.py. So similar to tuples, you can have all sorts of different data types. So this is people when I was first teaching the course. Now this is a different iteration, but I'm still going to use the same list. So here we see there's a bunch of strings. Here we see there's a string, an integer, a float, a boolean, and then a tuple within the list. So if we print these different things, oh, they're going to print exactly what we saw. It's going to print the variable. It's just printing the list out for us. The indexing for lists is very similar. So let's say we want to access this two specifically. We can say print list2, and then this is the last element. So we can say -1. And then within here, this is 0, 1. So this is 1. So that prints our 2 out for us. So the indexing is the same as strings, it's the same as tuples, it's even the same for slicing. So if you want to say like you only want 0 to 2, it's going to print only lamp and 3. And a quick note, so I did say 2, instead of doing 0, 1, 2, this is actually the number of elements itself. So I said starting at 0, I want 2 elements printed. So it's doing 2 elements starting at 0, which is why it only prints up to 3. So as I mentioned, tuples are immutable, so like you can't really edit them, whereas here you can actually edit stuff. So I can say list2 dot append. And append is a function that allows you to append or add something. So we can say we're going to append the number 25 and then print list2 again. So now we see that this is originally the list, but we've added 25 now. So we're able to change the stuff. So we can do that. There's also extend. So we can say list2 dot extend. And this is if we want to add multiple things. So we can say like 52 cat um, pillow 97. And then if we print list two, it's now added all of that stuff to it. So it has extended our list with all of those elements. So the one thing that I want to note is with all these manipulations, note that the order of this is completely preserved. So when we append something, it appends to the end. When we extend, it extends to the end. But what if we want to change a specific element or add something at a specific element? So let's say we want to actually make the word prince the first element. So we can say list2 dot insert. And then insert allows us to insert into the list. So we give it the index we want to insert. So 0 is the first thing, and then we give it what we want to insert. So insert at index 0 the word prince. And then we can print list2 again. And we see now that instead of adding to the end like everything else has done, prince has gotten inserted at the very beginning. Now, with that said, you can also change things. So let's say you're like, actually don't want Prince. We can change it. So we can say Prince is index 0. And instead, we can literally just treat this as a variable and say the element in list 2 at position 0, we're going to change this to princess. And now print list 2. So now instead, we've actually modified this item. We've changed it from prince to princess. So prince to princess. So that's the power of a list. Generally speaking, I effectively never use anything other than a list or a dictionary, which we'll touch on later. But yeah, it's lists are going to be the majority of the functionality that you need or that you use. Tuples are helpful, I think, in minor instances, but for the most part, I've never really needed to use a tuple in any situation that a list wouldn't function. So I generally defer to using a list when I'm trying to do something. So you can also, like, in addition to changing things, the lists are just really flexible. So like you can delete things. So you can say delete um, list2 0, and that's going to delete the princess that we added. So we'll say now it just deleted princess. So you can delete it. There's this really weird function called pop where it just removes the very last element. And I don't know the utility of that, but if you use pop, it'll do that. So um, list2 equals, or no, we'll just say print list2 dot pop. And so for some reason, it's just going to remove oh no, it just gives you the last element. Oh, that's a little different than the first time. It's like cutting. Interesting. So this just gives you the last element of the list, but I think if you save it, it'll remove the element. So anyway, yeah, as I said, I've never used this functionality for anything ever before. I'd probably just use like the -1 notation. So you can also do other things like formatting stuff. So if you have this thing called my numbers, 1 through 5, if you print my numbers, it prints the whole thing as a list. But if you just put an asterisk in front of it, it will print like normal numbers, like 1, 2, 3, 4, 5. So yeah. How much do we have left here? I think I might move the loop stuff to next time, the loops and the ranges. So for now, we'll finish up the list stuff. So you can turn strings into lists as well. And this is actually quite useful if you're trying to punctuate things. Like let's say you want every base pair to be its own element in a list. So it's like an A is its own element, a B is its own element instead of one whole thing. So we'll do that. So we'll say like A, C, G, T, T, G, G, C, T, whatever this is. And then it'll say my string split. Oh, wait, no, I need spaces. So I have spaces. So this is if it's like a sentence or something. So it will split it into its own element now. Alternatively, you can have these as commas and just tell it that's how you want to split it. Or there's not necessarily commas, but there's other ways you can do it. So like split, I think you can put an argument and it will say it'll split based on this thing. So if I say nothing, yeah, no, it won't do that. If I do commas here and then say split it by the commas, it will add each element as its own thing into a list. So this is really similar to like if you're opening something in Excel and it's comma delimited. Like you can separate it by the comma or separate it by the colon or separate it however you want and save each element into its own cell. So it's similar to that functionality. Um, so yeah, there's that. And then final wrap back around, we can do some simple math with lists. So let's say we have this list and we call it list D. So this is, for example, you read in one column of a data frame, and that's the column. You can find the minimum. So you can say print the minimum in list D. So just that min function, and it'll find the minimum. So it'll tell you the minimum is 1. You can find the maximum. So you can say print max list D, and it'll give you the maximum value, which is 10. You can also print the sum. So let's say you want to know what the full sum is for list D. You can do that and it adds everything and you get 55. So yeah, there's all sorts of simple statistics you can do. Um, and the thing that gets complicated is the reason I wanted to build up from like, this is text, this is a number, to stuff like this is because it all builds upon itself. So now we're looking at a data type, which is a list that has other data types embedded within it. So it's going to keep building upon itself, but I think for the most part, you're building a good foundation and understanding the different data types and organization and knowing that we can manipulate these different variables in different ways. So yeah, I'm going to pause there. I think I'll move everything else to the next session since there's a little bit left to cover with ranges and loops. So, are there any questions? All right. Well, it was nice seeing everyone.
Thank you, Vicky.